This is a talk which shows some new developments in quantum transport theory that have been carried out in these references you can see here. I'll try to cover 4 topics. It's a bit ambitious for an hour, but stop me for questions anyways. I don't have to go through everything. But the point about the Kubo formula is when it comes down to strongly interacting models where you cannot use perturbation theory and Fermi liquid theory breaks down and you're at high disorder, strong interactions, high temperature, lots of different regimes that are not accessible to analytic calculations. When you do numerics, you find that when you want to calculate linear response, which is a dynamic property, it's much more difficult than equilibrium response functions like order parameter, expectation values, correlation lengths, and so on, of static order parameters. These are thermodynamic quantities that you could use lots of techniques developed in statistical mechanics for quantum models and get a lot of answers. So theorists have been mostly concentrated on writing phase diagrams. Experimentalists, my advisor used to say experimentalists only know how to do one thing, is to measure I versus V. And he says every single experiment, in condensed matter at least, maybe in other fields too, is you put eventually some voltmeter and some ampere meter and you look at the ratio. And that means you're measuring conductivities, you're measuring thermal conductivities, you're measuring response through transport. But transport is difficult for theory to calculate. The only rigorous expressions for transport are the Kubo formula, and which is just linear response theory, assuming you have linear response. And that demands, as you can see, quite complicated calculations. So I'll write down the Kubo formula for conductivities in general. But before that, there's even a problem of defining currents. So I'll make my life easy. I'm working on open boundary conditions. So even in finite systems, you can define the current through the time derivative of the polarization. And that's much easier than trying to construct quantities like heat currents and so on. So what do I mean? I'm saying, first of all, you define polarizations. So let's say the charge polarization, let's say P of t, in the direction alpha, is simply, in a many-body problem, you sum over all lattice sides, so you could do an integral over space if it's continuous, and then you just write the position of that space and the density operator of that space and multiply by the charge E of the particle you're thinking about. And this is x of alpha, sorry. And this is just the dipole operator or the polarization operator that that is defined only on an open boundary condition. You cannot define it on closed boundary condition because there's no way to define the position on a closed boundary condition unambiguously. So you're restricted to open boundary condition. A thermal polarization, which is the father of the thermal current, as you can see, is, let's call it T. I'm following actually stuff that was done by Shastri a while ago. So thermal polarization is you do the same sum, you do the same position operator, but instead of the density, you look at the local Hamiltonian. The local Hamiltonian, there's some ambiguities in defining it, but any way you want to define it has to be such that you can write the full Hamiltonian as a sum over all Hi. So Hi can include local spin operators, momentum operators, and so on, but it can also include interactions, provided you split the interactions. For instance, you write half of Vij sum of all j. So this is well defined, but if you want the heat current, not the energy current, you have to subtract mu times Ni. Sorry, that's not here. That's not here, I'm sorry. That is the decomposition of the Hamiltonian, and here you write mu times Ni. So this is the thermal, or the heat polarization defined on an open boundary condition. Okay. Now, what are the currents? The simple electric current, I'm now taking Q equals 0, okay, uniform. Uniform electric current is just I times, I'm taking H bar equal 1, commutator of the charge polarization and the Hamiltonian. It's a time derivative of the dipole moment is the current, the uniform current, and the uniform heat current, JQ, is I, or JT, let's call it, H divided by P thermal in the direction of X. Finished. Now we know what the current operator is. You just take the Hamiltonian, commute it with this operator, I'll give you the full expression. This applies to magnetic problems, then you want to know the heat current in a magnetic problem. You do the same. You don't have to suffer too much to define the heat current. Okay, once you know the currents, the Kubo formula says conductivity is given by the response function S. I'm writing it in a general way for both heat and electric current, so O can run on C and T. The directions of the current can be alpha and beta, and the expression is H bar divided by the volume, so it's for any finite volume. Sum over N and M, these are the eigenstates of the Hamiltonian. Rho M minus rho N, these are the Boltzmann weights divided by En minus Em, eigenenergies. And now you have the matrix elements. So the matrix elements is N, J, alpha, O, M. No, let me start with M. M, N, N, J, beta, O prime, M. So by this I also cover the thermoelectric conductivity and the thermal conductivity, both longitudinal and transverse Hall. And here you have the energy denominator, En minus Em plus frequency minus I epsilon. So this is now a function of omega minus I epsilon, that's the frequency, and the volume, and temperature as well, but temperature goes into here. So rho M is e to the minus beta Em over Z. Okay, so I'm sure you've seen this expression. Now this expression has a correction term, very important, called the magnetization correction. It only applies for transverse coefficients like x, y. So let's say, gamma, epsilon alpha beta gamma, and there's a m gamma, O prime, and I have to divide by the volume also. Okay, what is this term? Well, this term is a very annoying term. It appears there because when one derives the Kubo formula for heat currents and thermoelectric, you get an extra term in the derivation that you have to subtract in order to really get the coefficient that appears in the conductivity. Just to write down what it is, so M charge is 0. There's no correction term for sigma xy. So sigma xy is given essentially by this expression where this is charge and this is charge. MCT, that's the alpha xy, the thermoelectric, M is given by I over minus I over h bar, expectation value of the commutator of the two polarizations, P of x and P, that's P charge of x and P thermal of y. Now, as you can just check by simple examples, this is not necessarily 0. And if you take a certain simplified model where the Hamiltonian site I is essentially P squared plus V of x, at the site I, if you take this kind of a local Hamiltonian, then you'll get that this is the expectation value of R cross the current J. So it's essentially the magnetization. That's why it's called magnetization correction. And it has expectation value, thermodynamic expectation value at all temperatures. This is an example, okay? So it's not the most general. So if you take a general Hamiltonian, you just have to calculate this quantity. But for a simple nearly free electron case or free particle case, could be bosons, or fermions, it's essentially this magnetization. And the other guy, the thermal magnetization, is minus I over h bar. And now the commutator is again between thermal and thermal, x and y. This is R cross J thermal. Okay, this has been a major source of headaches in the literature for a long time because one has to calculate it, and usually on the first term people do approximations. But turns out that is very dangerous because, because this term could be finite at 0 temperature, this term could be finite at 0 temperature, and you have to divide all this by temperature in order to get the thermal conductivity, for instance. And so let's write down the expression. So sigma xy is just SCC xy. Sigma, alpha xy is 1 over T S xy ct, and kappa xy is 1 over T S tt xy. So you have this 1 over temperature. So at low temperature, this diverges. So you can't have anything finite on these two sides in order to get a finite, or actually according to the third law of thermodynamics, you expect this to vanish at 0 temperature because entropy vanishes or heat also vanishes. And these two terms don't vanish separately. So there's a cancellation between them. Any approximations you do, whether it's analytic, you take an approximation of no disorder in one case, and you'll get essentially a non-cancellation and a divergence, and you can't use the approximation. So this is a problem that we will be solving later on. But this is the expression of the Kubo formula. And now I want to discuss why it's so difficult to calculate it. You look at this expression, and what you would like to calculate is the DC limit. Okay? DC limit is the low frequency limit of this expression. So the DC limit is defined very accurately in linear response. You take S at a finite frequency and a finite epsilon and a finite volume. You take the limit of volume goes to infinity first, then frequency and epsilon goes to 0 later. Okay? Otherwise, you get nonsense. You have to take this order of limit. If you want, if you have a finite volume, an open boundary condition, the first thing people will tell you, there's no currents passing through the system, right? Because you have a finite volume, so charges will reach the end, they can't go anywhere, conservation of current. How can you have a DC current in a system like that? Answer is you cannot. You have to take the volume to infinity. Now, if you don't take the volume to infinity, you take it to be very, very large, there is some kind of a regime that you can actually estimate the conductivity, and that regime is finite frequency. So if you want to think about it pictorially, you have essentially a table, finite table, and you have balls rolling on it, and you want to drive them. But you know you can't pass a current because they'll reach the end and stop. So what you have to do is you have to oscillate it. And when you oscillate, there is some response at finite frequency that in the limit of taking the system first to infinity and then take this frequency to 0, you'll get the DC current. That's the reason you have to do this order of limits. Okay? And that is something that people sometimes violate. Now, when is it violated? It's violated in cases that actually are justified. I should also mention that if I put a finite Q, I can also take a finite Q, not just finite volume, but I have to take first Q goes to 0 limit. Finite Q is actually not passing a DC current, but passing an oscillatory current at a finite wavelength. So you have a current going this way and that way and this way and that way, so not necessarily coming out of the edges, but you want to take Q to 0 first before you take the frequency to 0. Because if you take any potential at finite Q and put the frequency to 0, what will happen is charge will redistribute and not move, right? It's always a problem if you put a finite Q first. You take omega to 0 first and put a potential, finite Q, nothing will happen, no transport. So this order of limit here is also take Q to 0. Now, there are formulas, most of you might have met a lot, for instance, calculating Hall conductivities. Those formulas require strict conditions to be applicable. For instance, one of them is called the Streda formula. Sigma xy Streda, you might know, is EC dN dB. You look at this expression, it's been used in the quantum Hall effect, and you ask, is this correct? The answer, in general, no, but for the quantum Hall effect, it's correct. When is it correct? It's correct when you're allowed to replace the order of limits, because this is simply taking omega to 0 first, and then Q goes to 0 of sigma xy, Q and omega, or if you want, volume to infinity later. This order of limit is wrong, right? Wrong order of limits. But sometimes you're allowed to do it, and that is when the system has a gap, and then you don't care which order of limits you take, and then it's convenient to take the opposite order of limit because then you get a thermodynamic expression. So when is it allowed? Allowed when you have a gap, you're exactly at t equals 0, and there's no disorder. Well, no disorder means no disorder that closes the gap. So it's not a separate condition. And this is a gap from the ground state up. So this expression, and as well as the Chern expression, the Chern expression is an expression that sigma Chern is some kind of a integral over Aronow-Bohm fluxes. You take d theta x of psi 0, you take d theta y of psi 0, and you take the imaginary part, and you look at this expression, 1 over pi, something like that. It turns out to be quantized in full bands of single electrons. But this expression here has been very useful and been used a lot in the literature of the topological insulators that have a Hall conductivity, but they are insulators, also require these conditions. Okay? Once you have a metal, you can't use these expressions. That's very important to remember, because some people do. Okay. So what do we do about it? We want to, first of all, okay, and I didn't explain why this is so difficult. Why is this difficult? It's difficult for two main reasons. If you want to do ED, you have to know the full spectrum, and you have to calculate all the ENs and also all the wave functions. You know, even to get the ground state in a complicated problem is difficult. So this is very difficult. Second thing is, if you want to do Monte Carlo, for instance, maybe you don't have a minus sign problem, but you'll have to analytically continue imaginary time to real frequency and then take the limit, because the DC limit doesn't allow you to take 0 frequency, which would be just 0 Matsubara frequency also. It tells you, no, you have to have a real frequency and take it, this complex number to 0 last, after you took the infinite size system. And that's problematic. If you do analytic continuation from imaginary time to real time, it's possible for you to get finite frequency effects, but there's always a condition, and people who do that know it very well. Though for analytic continuation, where shall I write it? I have to erase the board. So for analytic continuation, you need that beta omega is larger than 1. Or let's say larger, the one won't be so strict. You need the frequency to be finite relative to the temperature. So even if you're interested at low temperature, you have to take the frequency higher than the temperature you're at. Now we are interested in DC, and that is why DC is so difficult. DC is always frequency goes to 0 in the end of the day, and if temperature is finite and you're interested in DC at room temperature or lower, or even at low temperatures, your analytic continuation doesn't work. So all these problems have made very few calculations for complicated model possible. And what I'm suggesting now is new avenues to actually crack this problem. And okay, we applied it to certain simple problems like hardcore bosons and the TJ model I discussed in the first talk. But I want to show you the general principle. So we look at this expression, it's ugly, both this and that. And there's a lot to be gained by formalism. I am not a formalist myself so much, but I find that sometimes when you compactify the expressions into a very simple formula or a formalism that has few letters in it, it allows you to understand better what's going on and also to generate expansions and generate results that will be very difficult to get otherwise. So the results I'm going to show you today, hopefully I'll get to them, will come from not using directly this Lehmann representation. Lehmann representation is the eigenvalue representation, but using hyperspace. And that essentially is the topic of what I'm going to discuss now. So this is, actually, this all was an introduction, so I... Yes, please. But let me erase while you talk, yeah. Ah, okay.
No, it's okay.
Okay.
Fine, I remember. So this scheme of linkings, it's only for finite systems, or because if you have infinite systems, do you run into some trouble with the polarization operator?
No, the finite system, you define a polarization on a finite system, but eventually you have to take the system to infinity. After you generate...
X is not something that the unit cell.
No, X is the position of the unit cell.
Right, so which is going
And it runs from minus L over 2 to plus L over 2.
And when you're taking L going to infinity, I remember that people who were doing polarization calculations in the FT,
Yeah.
they used to run into some trouble in the definition of the polarization operator because there is this term which is actually divergent to this R operator.
In real space they run a problem, or they do it in K-space?
In real space, if I remember correctly.
I don't see any problem in real space, but the problem is in K-space when you don't have periodic boundaries, and K is not a good quantum number.
Exactly. So then
But that's in K-space. Okay, in certain cases you can do it in K-space too, but the definition in real space. Okay, the definition is done in real space. No periodic boundary condition. That's the problem of K-space, right? Always assumes implicitly a periodic boundary condition on the lattice. But let's okay. So far, I'm not doing any calculations. I'm just massaging the expression, and eventually there'll be a calculation. Okay. So so I discussed that. Hyperspace. Hyperspace is a space of operators. I don't call it superspace like some people because particle physicists stole it for other reasons. Hyperspace is well known, has been used to generate approximations of Kubo formulas and so on for a long time. But it's a very clean and neat formalism that's not difficult for anybody who took quantum mechanics 1. What I'm defining is essentially a scalar product, two operators, A and B. A and B, I take what's called the Bogoliubov or Mori scalar product, which is writing it with some Hamiltonian given H, again as this rho m minus rho n, En minus Em, A dagger M n, B n m. Okay, why is this a scalar product? This quantity is always positive for every n and m, right? So this is always a positive weight. Here I can switch the n and m, and this will be A n m B n m star. So if you want, you can write it as weight of alpha, A star alpha, B alpha. As you know, if this is positive definite, it's positive semi-definite also, this is a kosher scalar product in Hilbert space. It obeys linearity when you add, let's say, B plus C or AB plus C or something like that. It will come out, and if you do it to the left side, you come out complex conjugate. It obeys, of course, that this is equal to BA complex conjugate. And, of course, because of that, AA is a norm. AA is always positive. And you can define now a Hilbert space of operators just using this scalar product with all the nice properties of Hilbert spaces. Okay, that's the first thing. Second thing is the Liouvillean. Liouvillean is the hyperoperator. It's an operator on operators, which I guess you all know. Liouvillean is the commutator of the Hamiltonian with whatever comes on the right. For instance, if I want to know time evolution by Heisenberg equation, I want to know how does an operator change with time. It's the Liouvillean times time times A. So you'll have all these nested commutators on A, you'll get the time dependence of A, right? That's the Heisenberg evolution. So if you see this, you see, oh, the Liouvillean acts like a Hamiltonian in Schrödinger space. Has a lot of similarities to that, except, of course, its eigenvalues are very different, but it's essentially an evolution operator of operators. Okay, the Liouvillean is something, okay, we have to know some properties of it. First of all, it's Hermitian. L is equal to L dagger. Now that requires a tiny bit of proof. You can prove it directly from this expression. So in other words, if you take A, L, B, and that's equal to B, L, A, complex conjugate, which is hermiticity, right? Transpose and complex conjugation will give you the dagger, and that's equal to L. So, okay, so it's Hermitian and it's evolution. Now, in order to relate to the Kubo formula, we also want to know how to invert the Liouvillean. Inverting the Liouvillean, let's say 1 over L, is a tricky business. You have to have some epsilon prescription to be able to invert it. So let me invert the Liouvillean and just do brute force inversion of a simple operator. That's equal to 1 L divided by L squared plus epsilon squared is the real part, plus I epsilon L squared plus epsilon squared. This is called 1 over L real part, and this is called 1 over L imaginary part. If you look at the content of these guys and you put it in the eigenbasis of the Hamiltonian, L in the eigenbase is very simple, right? L, let's say between, so L times A, if you write it in the eigenbasis, and M is simply En minus Em times A and M, right? That's essentially its eigenvalues in this basis are En minus Em. So the effect of L is just to multiply by this difference of energies. So L always takes these differences of energies. Now, if you look at this expression, it tells you that this guy will be really 0, right? If you take epsilon to be very, very small, it'll go like 0 unless En and Em are close within a distance epsilon to each other. And then it becomes actually large. It's like a delta function of En minus Em, right? This becomes like a delta of En minus En, to be precise, times pi. This guy is like the principal value. Now, the whole trick of doing the Kubo formula correctly in the DC limit is to keep the epsilon finite, not allowed to take it to 0. So I'll keep it finite. But even if I write an expression like this and like that, remember there's an epsilon here. Okay? So now I want to write the Kubo formula in a much nicer way than was written than this guy. So, no, from the Kubo formula. So, let's take SOO alpha beta, write it as h bar divided by volume, imaginary part, and instead of the lemon representation, write it just as JO alpha, JO prime beta. These are the two currents. And in the middle, 1 over L minus epsilon minus I epsilon here. This is all. So it's essentially like a Green's function in Schrödinger space. Instead of Green's function, you have a Liouvillean and you have the frequency, and you just have to evaluate it. And now I'll do the following. I'll first of all concentrate on XX terms, like sigma XX, alpha XX, and kappa XX. And these two guys will be either the same, or will be the same direction at least. And you can also symmetrize it and be the same operators on both sides. And you'll have this 1 over L. And then when you take the imaginary part, so let's do it. So sigma XX is going to be h bar divided by v. And the imaginary part will go into essentially the imaginary part of the inverse Liouvillean. So it'll be j 1 over L minus omega imaginary part, j, let's say this is charge, so no label. That's the expression for the sigma xx, okay? So this is a very convenient expression to expand in what's called continued fractions. And I'll explain the expansion now. The expansion in continued fraction will allow me to calculate this quantity as a function of frequency at all temperatures, because temperature is just the property of the scalar product here. At all temperatures, all frequencies, but it will be calculated using essentially the equal time static correlations. Continued fractions have a problem that one needs to know an infinite number of them in order to really know this function, but there's ways of extrapolating the numbers that you get from low order calculation. And I'll show the continued fraction of sigma xx, which also applies to alpha xx and kappa xx, if anybody wants to take it there. So that is the purpose here. I should emphasize that for the Hall effect, when here you have x and here you have y, and you want to be antisymmetric with respect to x and y, there's no continued fraction that I know of, and one has to use different methods to get the Hall effect. But for longitudinal, there's continued fractions. Okay? So any questions so far? Yes.
What is the name of this scalar product again?
Okay. I learned about it when I saw the proof of Mervin-Wagner theorem using essentially the scalar product by Bogolyubov, or essentially it was first by Bogolyubov inequality, it was called. But then in the literature, I found that the ones who really made use for it for the Kubo formula was Mori. So maybe you call it Kubo and Mori, I guess. I guess both were in Japan, so they talked to each other. It was later used also for generating, in the German school, this thing called memory functional formalism. But memory function formalism is only the first continued fraction expansion. But the continued fraction expansion is actually, could give you much more knowledge, much more information from the Hamiltonian than that approximation. Okay, so I'll do the continued fraction. The continued fraction is extremely easy once you write it this way. In most places in the literature, I didn't see it actually develop in this very short way because they didn't use the hyperspace formalism. But it's an old subject. Okay, so continued fraction is trying to invert the Liouvillean in order to calculate the Kubo formula. And the idea is to define a set of operators called a Krylov basis from the current operator Jx. This is actually Q equals 0 Jx that we defined before. It's an operator. It's sum over hoppings on bonds, if you want, in a simple hopping problem. But in general, this is an operator here we know, and we want to create whole basis. So first of all, we create the root basis. We have to normalize it. So it'll be Jx divided by Jx, Jx. Jx, Jx is a special quantity we need to define. It's essentially the susceptibility, autosusceptibility of the current using the Bogolyubov formula, and it's essentially the optical sum rule or conductivity sum rule. if you want, you can show that's equal to d omega over pi sigma xx of omega integrated from 0 to infinity. This quantity here is, if you take electrons, even with interactions, even with disorder in a band structure, it will be n over m. If you remember this expressions from band theory, or n over m star. So this quantity here is the norm of J. You divide by the norm of J, so it's a square root of that, and you get the first Krylov base state. The second one is just Liouvillean times 1 normalized. And now, iteratively, you can create n plus 1 from taking the Liouvillean times n, but subtracting a piece which is n minus 1, and normalizing. What is this piece? This piece is called recurrent. Recurrent. And in order for this to work, what does it mean to work? I want to generate an orthonormal basis. So n over m is delta n m. In order for this to apply, all you need is that delta n is simply the matrix element of the Liouvillean between n plus 1 and n and n minus 1. Okay? That's, if you can easily check. If you apply n minus, let's say you apply n to here, okay? Just a second. If I apply n to here, then I have, you can show that L expectation value in the same n is 0, and based on this construction. But then you have here n and n minus 1. Just a second. How do I do it? No, I'll take here and multiply this by n minus 1. Sorry. If I multiply this by n minus 1, I'm assuming now that this is orthogonal. This is 0. And it will only be 0 if here you'll have n minus 1 ln, which, because it's Hermitian, will be the same value up to a phase, but we don't care about that. And then you'll get that this is equal to that, because there will be 1, and this will be L. Delta n will be equal to this expression. So I'm not going through this whole proof very slowly, because it's not difficult and easy to confirm. So once you know that this Liouvillean matrix element in the Krylov basis is delta n, you can write the full matrix L in the basis nm. How does it look like? Well, I said the diagonal terms are 0, that you can verify. And then the off-diagonal terms are delta 1, delta 2, delta 3, and all the rest 0. So it has a very simple representation, the Liouvillean, as a tridiagonal matrix. If you want to think about it, it's like a hopping model on a half chain, where the coefficients of the hopping are different on every hopping. And one is interested in essentially the Kubo formula. So sigma xx as a function of omega will just be, first of all, the normalization, chi CSR, this optical sum rule, 1 over L as a matrix evaluated between 0 and 0, right? So this is the norm of the two J's. And this is just the matrix, L inverse, evaluated at 0, 0. So actually, let me write it with a frequency, L minus omega. So if I put here minus omega, minus omega, minus omega, and I want to invert this matrix, take it to the minus 1, and evaluate it at 0, 0, you do this elimination by rows and columns sequentially, and you can show that it's equal to 1 over omega minus delta squared times the inverse of the rest of the matrix. So it's going to be chi CSR 1 over omega minus delta 1 squared times the inverse of the rest of the matrix. But the rest of the matrix has the same form, omega minus the rest of the matrix. Omega minus the rest of the matrix, ad infinitum. Okay, so you look at this, and don't forget, every omega has a small I epsilon in it. Now, it turns out that I epsilon is not important if the delta 1 is finite, delta 2 is finite. So the I epsilon doesn't matter here, but it does matter that there is an imaginary part to all this business, because what I'm interested in is the imaginary part of this. So you have to invert this matrix. Okay, so now come the question of how do you calculate deltas, and then how do you evaluate the continued fraction? Two problems. So first of all, calculating the deltas is very easy if you know the moments. What is the moments? The moments, mu 2k, is just jx, L to the power 2k, jx. It's just the matrix element, if you want, 0, 0 times CSR, but this matrix here to the power 2k. So it's chi CSR, and then L to the power 2k. Now L depends on all the delta 1, delta 2, and so on. But when you take it to the power 2k and evaluate it at 0, 0, not all of them will come in, because it's a tridiagonal matrix. You take the square of it, and you'll see what appears here on this point. It'll be the delta 1 squared. But if you take the fourth power, you'll get delta 1 to the fourth power, but also delta 1, delta 2, delta 2, delta 1. And the higher moment you get the more recurrence coming in. So this is an algebraic expression that's easy to do in Mathematica. And what you learn is that mu 2k depends only on delta 1. So this guy depends only on delta 1 up to delta k. So you have expressions. Mu 0 is equal to chi CSR. Mu 2 divided by chi CSR is delta 1 squared. Mu 4 chi CSR is delta 1 to the fourth plus delta 1 squared, delta 2 squared, and so on. All these are well-known expressions, but once you know these guys, because it only depends on lower values of delta, you can solve. You can do, first of all, you can plug in here and get delta 1. Once you know delta 1, you can, if you know mu 4, you get delta 2, and so on. So that's why you do it. You get those deltas, and you put them in a continued fraction. Now, each one of these calculations is a thermodynamic calculation. If you write it explicitly, it's the susceptibility between H, or if you want to write it as an expectation value, it's the expectation value of a commutator of J with H, 2k minus 1 terms, 2k minus 1 nested commutators, expectation value. These are all operators evaluated at equilibrium at any temperature by any method you want, and you get those mu k. And okay, once you get the mu k's, you get the delta, you put the delta in, and you start getting an idea of how the continued fraction behaves. Now comes the point of extrapolation. What you plot is the order n, and here you put 1, 2, 3, 4. Now, of course, the higher order you go here, the higher order moment you have to calculate, the more work it is. So you want a finite number. You don't want an infinite number. But you need an infinite number to get the full function here. This is called the moment inversion problem. So here comes the acquaintance we have with different continued fraction expansions for different functions. And those actually tell you quite a lot about the behavior of the functions if you look at the recurrence. So I'll just give you some examples, and that'll be enough. Now, anybody who wants to get a full library of translations from continued fractions to functions is welcome to look at Viswanath book, Viswanath. It's called the recursion method. In many-body problems. In many-body. Excellent book. It gives a lot of intuition. But you can also play with it. You can take functions you know, and look at their continued fractions, look how they behave. For instance, if you take just a straight line, this is delta n squared. And let's say delta n squared, so this goes like n squared times, so delta n squared goes like n, times omega squared. If you have this kind of a slope with a omega, then the function is simply a Gaussian with some coefficient. Normalization is not difficult to get. It's That's one function. Another function, that's the one that actually was used most in the extrapolations by the full day and these different memory functional ideas. So let's say I take a different function. I take a constant. So here delta n squared is just omega squared. This will give me sigma xx that goes like omega squared minus small omega squared square root theta function of omega squared minus omega squared, which is a semicircle. So this guy looks like that. This guy looks like that. And now comes more interesting functions. What happens if it's not just one peak, or let's say the function has a low tail behavior that goes to 0. Let's say it's not a Gaussian, but it's a Gaussian times a power law. So let's say this is omega to the power beta. Or you can have another guy that diverges. Let's say it wants to be a superconductor. So this is omega to the power, let's say, alpha less than 0. And this is beta larger than 0. Then all this changes, but in a very delicate way. For instance, in the case of beta larger than 0, so let's call that white and this call that red. So what will happen is, if the system wants to go like that, then this will go up and this will go down. This will go up and this will go down. There will be an even-odd effect that was proven analytically, and the amount of even-odd effect depends on this power beta. And if you invert beta to be less than 0, the even-odd effect gets reversed. So you can tell by whether the odd or even are larger than whether the odds are larger than the even or even larger than the odd recurrence, whether the system has either a pseudo gap or actually has a very high conductivity at low frequencies. So it's, even though we're calculating certain finite number of moments, the analytic assumptions that are made by extrapolation tell us about the low frequency part as well as the high frequency part. So the overall slope will actually be dependent by the high frequency fall off of the Gaussian. But the even odd will tell us about the low frequency. And I just played with it yesterday a little bit by taking, for instance, an example of if you have a pole, a collective mode. Talk about Higgs and stuff like that. So if you have like something that looks like that, but then you have a delta function. Well, if you have a real delta function, and this is, let's say, a semicircle or something like that, then the continued fraction looks like the same as the continued fraction of the semicircle, but the first moment, delta 1 is off, is high. Just curiosity. This was used in a very nice way to prove the existence of a plasmon in a Coulomb gas by doing the recurrence and finding that the only thing that changed from the Coulomb gas to the neutral gas is one recurrent. Okay, something you don't see in the moments, you don't see in the perturbation theory or any of these things, but I think it's the most rigorous proof of the existence of a plasmon at Q goes to 0 limit that you might find interesting if you want to teach it. Anyway, so that's continued fraction. So the extrapolation, if you are really interested in doing a calculation and you have a finite set of moments, the extrapolation is to use some kind of a function, variational function of sigma, which will have an infinite number of recurrences that you can calculate analytically. And so that will be your variational function. But how would you find it? You would minimize least square fit of the variational function with the finite number of moments you calculated. So if you have, 10 moments and you have 3 or 4 parameters, you can, if it fits, then if you get the two recurrents of the two functions, the real one and the variational one, to come very close to each other, then you have a good estimate of the function. And I think that's the best you can do, but it's it's self-fulfilling. In other words, if you're successful and you found the right function, calculate 1 or 2 extra moments and see if they fall on the same line. And if they do, it's like any numerics, then you know you've converged. So that's just a, tips, because that's a technique we used for disordered bosons in one dimension in the context of disordered interacting systems, the MBL problems, and so on. But what I'm saying is that there are perhaps many different ways to extrapolate, but this is one suggestion we give. Okay, now comes the question of Hall. So let's say we know how to calculate sigma xx, we want to do sigma xy, and one of the problems we face when we look at the Hall coefficient, besides the magnetization correction, is when you take the imaginary part of the Hall, you end up with an expression that a priori looks like it demands, in the Kubo formula, all the eigenstates. And so in the sigma xx, we had jx 1 over L double prime jx. And that was the imaginary part of the expression, because these are complex conjugate matrix elements that give you an overall positive contribution, and this will be the only place to put the imaginary part is on the inverse Liouvillean. But sigma xy has 2 contributions. One of them will be, taking the imaginary part, will be taking this guy, so it will be jx 1 over L imaginary part jy. But then there's another term, which is taking, if you want to write it in the Kubo formula expression, rho minus rho e minus e, jx, jy, and m, n, and m, here to take the real part. Minus, plus omega. So you take the imaginary part of the numerator and the real part of the denominator. What's the problem a priori that looks like when you want to calculate that? This decays very weakly with En minus Em, just as 1 over the distance between the energies. So even if the 2 density matrices project you onto the ground state and a few excitations, this is many-body, right? So it's, let's say it wants to be very close to n equals 0, and m also wants to be close to m equals 0. So that's not enough, because you can have here rho n, but here Em could be high up. What's the problem with that? That's a problem that, first of all, you have to calculate lots and lots of eigenvalues to calculate the Kubo formula. Second problem is that you can't use effective Hamiltonians, which is my favorite way of attacking problems, because you're sensitive to high energy excitations of the original Hamiltonian. But what I want to show is that that this expression is correct, actually, but it's not true that it's off-shell. So I'm putting here off-shell, depending on high energy, depending on En large. Okay, so is it off-shell? The answer is no, but it's surprising. Okay? Especially because this expression has been used to derive the Chern formula in a periodic boundary condition. But on open boundary condition, this expression will give us an on-shell expression, and we'll see how it works. So, first of all, what about this term? This term here is not a Hall coefficient. Why? Because it's symmetric in x and y. And a Hall coefficient have to be antisymmetric. That's the definition. The symmetric part is really just if you have no C4 symmetry and your sigma xx and sigma yy are not the same. So you have a tensor which is all symmetric in terms of magnetic field, and also xy and yx are the same. And you just rotate your axis so you eliminate those guys, and you get you get 2 different values. But if you have a C4 symmetry, then these guys have to vanish. C4 symmetry. This guy is antisymmetric under C4. In other words, if you take x and y and replace one by the other, you get minus. And it's also antisymmetric with respect to magnetic field according to Onsager relation. So this is really the whole. So I just now write down the expression of the whole in hyperspace to avoid all the horrible notations of Lehmann representation. So it's going to be Jx 1 over L real part, Jy imaginary part. I'm taking the full imaginary part, but here I took the real part. And this is the whole coefficient. And this is true also for the alpha xy and the kappa xy, just putting the right operators here. Okay. Now I'm using a trick, not a trick, but an expression. AB as a scalar product could be written in hyperspace as minus trace rho commutator of 1 over L real part A dagger, commutator with B. Now, you have to believe me that this is equal to that. You can see why. 1 over L will give me this En minus Em that we had. The commutator was actually from rho. Remember, there's a rho n minus rho m. So it's a commutator between rho and this guy. But I can pass the commutator into these two operators and leave it as a thermodynamic expectation value. But the thermodynamic quote-unquote, this looks like minus thermodynamic, right? When you have trace rho something, it's a thermodynamic expectation value. So it's commutator of 1 over L prime A dagger B. And then you can say, well, is it useful? It's useful for derivations. But when I say quote-unquote thermodynamic, what am I missing? Thermodynamic is epsilon equals 0, but here there's a small epsilon. And that's very important, okay? So I do keep the finite frequency. I'm not taking the frequency to 0. Okay, so this is just a way of writing the scalar product. And when you write the whole coefficient, it becomes minus trace rho, commutator between 1 over L Jx, 1 over L real part Jy. Okay, so far I didn't simplify much because inverting the Liouvillean, as we learned, is not easy, but I wrote it in terms of this commutator. Okay, next step is to evaluate the 1 over L Jx. So 1 over L prime Jx, I'm being very careful about the epsilon, is L divided by L squared plus epsilon squared, right? That's the real part of this inversion. And now Jx, allow me to write it as L times Px, right? That's the definition of the current from the beginning. So I have here, these all commute with each other, so I can put L squared Px, which is equal to L squared plus epsilon squared divided by L squared plus epsilon squared, Px, which is just Px, right? Minus epsilon squared divided by L squared plus epsilon squared Px. Okay, this is just Px. So I got the polarization. This guy is the Degeneracy-Projected Polarization. Look what this factor does. If Px is acting between two eigenstates that have very different energies, this is 0. But if it acts in the manifold of degenerate states, okay, if En is very close to Em, this is close to 0 and this goes to 1. So it's like a theta function. It's not a Dirac delta function, it's like a theta function that acts in a window of epsilon and only keeps degenerate eigenstates. So let me call it P tilde of x is degeneracy projected polarization, TPP. Okay, so I'm writing it this, and what it'll give me? It'll give you minus trace rho, and then here P minus P tilde of x, commutator with Py minus P tilde of y. Okay, and I'm expanding it, so I get minus trace. Actually, there's a plus here. Why is it a plus? Because I forgot the I here. Yes. The current is I times LPS, right? It's I times the commutator. So I have a I here and an I here. So that will take this to be a plus. Okay. Now this expression here is simply written in terms of, okay, I can convince you, since this is a projected polarization, if I commute it with a non-projected polarization, but I take the expectation value in the eigenstates, it'll be as if I made this tilde, non-tilde, exactly the same as tilde, tilde. So you have here one non-tildes, which is px, py, the commutator of the two non-projected polarization. And then I have two with a minus sign and one with a plus sign. So it'll be overall one with a minus sign. Trace rho p tilde x, p tilde y. Okay? And that's the expression. This expression is much, much simpler in many ways than the original Kubo formula. Why? This guy, in open boundary condition, for electrical current, electrical polarization, it's just a commutator of x and y. There's no magnetic field, there's no curved space here. The two polarizations commute. This actually takes most of the Kubo sum, which actually vanishes. These guys are projected polarizations. They only live in degenerate subspace. And if we take low temperature, it'll be only the ground state and low-lying excitations that care, where these operators are non-zero. And because it's projected, they don't commute necessarily. And just to give you an idea why they don't commute, we can think about the electrons in Landau levels. Electrons in Landau levels, if you remember your Landau levels, are just written in terms of two operators that commute with each other. One of them is called pi, and the other one is called r, the guiding center. So I'll write down the expression of the position operator in the magnetic field problem. H is equal to pi squared omega c, plus, yeah, that's, I guess, that's the Landau level operators, right? Which will give you n plus a half times omega c. I think it's omega c squared here. Yeah. And then you have, okay, that's the Hamiltonian. And you have x is equal to r of x plus z cross pi. And I think to get the right dimensions, this is dimensions of distance, this is 1 over distance, so you have lb squared there. Okay, in the y, so it's z in the x direction. So you'll have here rx, and here you have pi y. And y will be the other guy. So if you just write it as a vector, it's just this vector. Okay, this decomposition is very nice because r with pi commute, and that's why you don't have any, you have degeneracy in the Landau level, which is dependent on the quantum numbers of r. But it also, because pi will essentially be the raising and lowering operator of Landau levels, this goes into n plus a half omega c. This raises and lowers n, and that means it's not degeneracy. It's not acting within a degenerate manifold. It's between degenerate manifolds it's acting. So if I want to know what is x tilde is just r. Because this guy is inter-Landau level. Inter-Landau level, and this is intra-Landau level. So the degeneracy-projected polarization in the Landau problem is just the guiding center. And guiding centers do not commute. Rx with Ry, commutator, if you remember, is minus I times Lb squared, which is something that looks like 1 over b with right units. And if you look at this expression, you'll get the density n divided times EC over b. You'll get the correct result. So the degeneracy projected polarization are essentially the important objects that determine the Hall coefficient. Now, this is open boundary condition, and therefore it arrives at some result that tells you that if you have a finite sigma xy, if this is non-zero, then there must be low-lying excitation in the problem above the ground state at a distance smaller than epsilon. In other words, sigma xy non-zero means existence of gapless chiral, because the polarizations don't commute, so px and py act like momentum and position. So when you draw, the wave function, its position will tell you whether the current is going left or right. That's a chiral state, gapless chiral extended states. Okay. So if you're in a metal, those chiral extended states are everywhere in the metal. But if you're in a quantum Hall system with open boundary condition, it means you must have edge states that are chiral that will carry essentially all the contribution to the Hall coefficient. Okay? Okay, so this is an interesting result that also applies for alpha xy and kappa xy, which previously I didn't see any theorems for that. But what I'm saying is that the advantage here is not just giving you a numerical, easier method to calculate sigma xy, because now you only have to calculate very low energy excitations. You could use an effective Hamiltonian to describe them, and you only have to go to the ground state and a few excited states. You could use DMRG or whatever favorite method you have for getting low energy states to evaluate this without too much pain, unlike the original Kubo formula. And the most important thing is that if you're talking about the thermal effect, what about the thermal magnetization? The thermal magnetization, OO prime, as I said, was just a commutator of the polarization. So this guy will just completely cancel this guy. No need to calculate it, and no need to worry about divergence at low temperature. Just calculate this guy. Okay? How am I doing in time? I don't want to...
Well, I mean, if you could wrap up in 5 minutes, I think that would be good.
Okay, okay. 5 minutes is good, just to mention the final formula that was the Hall coefficient that allowed me to do the Hall coefficient of the TJ model. Notice that for here, still, I need to diagonalize the Hamiltonian. I need to get some eigenstates. This is not the preferred method to get the Hall coefficient. But the Hall coefficient itself is actually a luck. It's kind of a situation where the epsilon dependence, that's the major source of problem here, drops out. There was a question about scaling of L and epsilon, but maybe I'll leave that to question period that I can explain. But let me just do the Hall coefficient. What is the Hall coefficient? The Hall coefficient is not the Hall conductivity, but it's the Hall resistivity derivative with respect to magnetic field at magnetic field equals 0. So it's a very special limit, but it's still a transport quantity. It's still a property that one should, in principle, calculate sigma xx, sigma xy, take the difference. So let's say the Hall coefficient is d sigma yx dB divided by sigma xx squared. Now, since this is linear in field and this is quadratic, I don't need to take here another sigma xy and just evaluate this at b equals 0. So this quantity here in Drude is 1 over NEC. Okay. But if you evaluate d sigma xy dB using the formulas I did before, you'll get d sigma yx dB is jy, 1 over L imaginary part, magnetization, which I'll define soon, L imaginary part, Jx. It's this horribly looking susceptibility that has, if you want, all these operators, hyperoperators acting on Jx. M is just minus the HdB, which is the operator of magnetization, commuted with everything on its right. So you look at this guy and say, how in the hell am I going to calculate that? So first of all, it's on shell. Okay, that's one thing that's nice, because these guys project you on shell. This is also on shell, and then there's, you know, some temperature dependence, but overall, you don't need to go to high energies to calculate it, and you could use effective Hamiltonian to replace the Hamiltonian and replace the currents and replace the magnetization. Once you do that, like in the TJ model, you have an expression that you can calculate. Okay, but still, this is difficult because it has, if you want, continued fraction expansion or something very complicated of all these recurrents. But what you could do is insert, that's why the Hilbert space is so useful. You can insert a closure of states, of Krylov states. This is built out of X, and these guys, M, is built out of JY. If you insert these two guys in here, you'll get a double sum. And the double sum will have one term that's really nice, which is just 0 and 0. So that term I keep separate. That term would look like JY M JX. That's the 0, 0 term, right? Because you have, that's the 0, 0 term. And all the rest of it, and this will be times sigma xx squared. Why? Because you have jx and jx on this side. So it's just the sigma xx squared. One sigma xx from here and another sigma yy. So it's actually sigma xx times sigma yy. But you have C4 symmetry. I write it this way. Now I have to divide by sigma xx squared. But there's normalization. So here I'll also need, I'll need to divide by chi CSR squared. So these two guys cancel. And you're left with just a sum rule. I showed you how it's just a JJ norm and this matrix element thermomagnetization. That is called RH0. And that's calculable. And then you have correction terms, which are taking all the rest of the all the rest of these Krylov bases. So you have N, M, and you have essentially the Green's function, if you want, from, let's say, 0 to N. That's a Green's function, right? Imaginary Green's function. But it's a tridiagonal matrix. And there's properties of tridiagonal matrices that are very simple. The Green's function from 0 to N is the same as the Green's function from 0 to 0 times a factor of hopping between 0 and N. So I'm just giving you the answer. So you have R, N, R, M. Actually, only the even terms matter, so it's R, I, R, yeah, R, oh, okay, R, N, R, M, and then you have the matrix element of the magnetization between N and M, 1 over chi CSR, that's the correction term. And what are the N, Rn? Rn is delta 1 divided by delta 2, up to delta 2k minus 1 divided by, or let's say, n minus 1 by n. And this is even. This is even. This term is complicated. All these matrix elements require these Krylov bases. You have to do the commutator and get these operators. So it's chunky operators that you have to evaluate its susceptibility. But it's still susceptibility. It's still expectation values in the thermodynamic equilibrium. All these are recurrents, which also are expectation values. So in principle, all the expression here is thermodynamic. There's no epsilon dependence. There's no analytic continuation needed or anything like that. Now, the hope is that these guys are small. In other words, that you get most of the answer from the first guy, and you calculate the second guys and see how they are large and how they converge. Now, it is supposed to converge because this guy is supposed to be finite. So this guy is supposed to converge. It can't be infinite if the left-hand side is the finite Hall conductivity. But one has to calculate. Our achievement was in the TJ model to calculate the first 3 terms and find that they're really small. They're like, like 5% of the first term throughout the doping regime. In hardcore bosons, they converge less slowly, close to half filling of the hardcore bosons. And they give essentially a correction of order half for the first term, and then a quarter, and a smaller term for the fourth term. We went up to fourth order. But it's quite a difficult calculation. My postdoc, Sauri, is just now finished it. But it converges a bit slower. But at least it's controlled. One can always go to a higher order and see whether the truncation is justified. So that's what I have to say. So I think by that I exhausted your patience, and you can answer questions if you want.